Hello students, welcome to the next lecture on the numerical analysis. Today we will discuss about the various examples related to Newton-Raphson method. This is a part 1. After that we will cover the part 2 where we have solved the more 10 examples in here. In this lecture we will discuss about when the Newton-Raphson methods failure, what are the special cases of the failures, and the various 10 examples are here. Myself Dr. Harish Garg. You can simply follow my YouTube channel Dr. Harish Garg for finding the various lectures on numerical analysis. So what is the Newton-Raphson method? As we discussed in our last video, this method is used for finding the approximate root of the equation f of x is 0, and the iterative scheme is used for the Newton-Raphson method is my here. In our last lecture we derived this one, we discussed the convergence condition, we also discussed the order of the convergence, which is come to be as a 2. The order of the convergence condition we all find in our last lecture. What is the algorithm for finding this? If you have a continuous function f such that the function value at the end point is less than 0. What is the meaning of that? The f will satisfy intermediate value theorem. Fine. So once the function will satisfy the intermediate value theorem, then we can apply these 3-step rule for finding the root of this equation. So let I is the interval like a comma b in which the root lies. So make sure you have to firstly find the interval a comma b. If the x0, that is the initial guess, is already given to you, then there is no need to find this interval a comma b. But if the initial guess is not given to you, then you have to firstly find the interval a comma b and then choose x0 in between a comma b. Then you can choose any x0 in between a comma b. So what is the first step is, you have to choose any initial choice x0 in the interval I, and then we can apply this iterative formula. Based on this x0 we can find the value of the x1 from here. Based on this x1 we can find the value of the x2, we can find the value of the x3, and so on. We can continue this until the difference between the two values, consecutive values, like x3 minus x2, x2 minus x1, x4 minus x3, and so on, will be less than of the desired accuracy. Once it is the less than of the desired accuracy, then we can say xk is my root and stop the process. Otherwise we will go to the back to the step 1, or we can go back to the step number 2, and then we can find its solution. Remember, this is called as the absolute error. You may change them to the relative error as per your statement choice. So let's start with this one. We will describe the 10 examples in this lecture so that you can understand the concept very easily. Now first of all, you can check whether the initial guess is given to you, whether the initial point x0 is given to you. No. So it means your first target is to find a comma b. How you find this value? We can check about the intermediate value theorem. What is the intermediate value theorem? For this function, if I consider this is my function fx, then we can find the value. So say if I consider 0, what is the value of 0 is minus 5, which is less than 0. Fine. So I need one more value, say f of 1. What is f of 1 is 1 minus 2 minus 5, which is again less than 0. We have to find the 2 points such that they are of opposite sign. What is f of 2? It is 8 minus 4 minus 5, which is again less than 0. What is f of 3? It is my 27 minus 6 minus 5, which is greater than 0. So what is the meaning of that? The root lies between, what are those? These two numbers are opposite signs. So we can say the root lies between 2 and 3. Remember, you can also write the root lies between, because this is a negative, this is a positive, you can also say 1 and 3, or you can also say between 0 and 3 as per your own convenience. But you can see the length of this and this is larger than of this, so we always prefer the interval which has a smaller length. So I can say the root lies between 2 and 3. Now you have to use the Newton-Raphson method up to the 4 decimal places. So n is my 4. So once the n will be my 4, so the error will be as I describe you in the bisection method and other, where n is my number of the decimal places. So you have to find the error up to half 10 raised to power minus 4. Why 4? Because n is my 4 decimal place. Now we can found the sequence x1, x0, and send until this condition met. So for that we need firstly the derivative. We can find the derivative of this point f dash. Fine. Now our target is to choose x naught. So firstly I can substitute this value at here. So what will happen is I can take the LCM, we can get as this expression. Now you can choose any x naught in between the 2 and 3. You can choose any x naught in between 2 and 3. So let's say I choose x naught as a 2. Substitute this value x naught 2 as here. So it will be 2 raised to power cube plus 5 divided by 3, 2 raised to power square minus of 2. So after the calculation you will get as 2.1. Now clearly says x1 minus x naught. What is the difference between them is 0.1, which is not less than of this condition. So it means we need to find the x2. How you find x2? I can substitute this value here. This is 2.1 cube plus 5 over 3 times 2.1 square minus of 2. After the calculation you can get this value. We will check whether x2 minus x1. What is the x2 minus x1? Clearly say this is a 0.01 something, which is not less than of this. Then we can find the value of the x3. I can substitute this value of x2 as here. We will get this number. And clearly says if you take the difference, it is less than of this number. So therefore we stop the process, and this is my right answer. I can convert into the 4 decimal places. What is the 4 decimal places is my here. So these are my right answer. Now again in this case we have to find up to the 4 decimal places. Again the initial vector is not given to you. So we can firstly start with this. So clearly says, again remember, whenever you have the sine, whenever you have the cosine, tan, secant, any of that trigonometric function, you have to set your angle in the radian. Fine. In your calculator you have to set your answers or your angle as a radian. Now what is the sign of 0? You can see 0, sign of cos of 0 is 1, which is a positive. Now we have to find the number which is less than of the 0. So how you can do that? If I consider as a pi, so you can see sin pi is 0, cos pi is my minus 1. So it means the root is lies between 0 and pi. I need the derivative. We can find the derivative of this, which is the product rule, that is the x cos x plus sin x, and it is my. I can substitute this value at here. Now if you take the LCM, does it cancel out? It is not cancel out, or then there is no need to take the LCM. I can simply separate them. It will be tan and of this. Fine. Now you can take any number in between them. Remember, it's a 0. What is the pi is? 3.1415 and so on, because we need up to the 4 decimal place. You can choose any number between 0 and 3.1415. So I suppose as a pi. I can substitute this value here. What is my this first condition is, when you substitute this, what is that? If I found for this is the pi, this is my tan pi minus 1 over pi. So tan pi is my 0, so this is pi minus 1 over pi. Use the calculator and calculate it at here. Remember, since they are talking about the 4 decimal places, you always, if they are talking about the n decimal places, you can measure the result up to the n plus 2 decimal places at least. Now based on this x1, I can substitute here. We can find the value of x2. Clearly says we need up to the 4 decimal places, so the difference of them must be less than of half 10 raised to power minus 4, or you can see the 4 decimal places which are not matched. Then we can find the value of the x3. We can find as x3 and then x4. Clearly says up to the 4 decimal places they match. Fine. Up to the 4 decimal places match. If you find the error, it will be less than of half into 10 raised to power minus 4. Or you can simply say x4 and x3 are same up to the 4 decimal places. So the right answer are my here up to the 4 decimal places. So I can round off them to be 4. Again you can see the initial solution x0 is not given to you, so we can find the interval. So how you can write that? I can rewrite this. What is the f of 0? It's a 0 minus 1 less than 0. What is my f of 1? E raised to power minus 1, which is 2.718 minus 1, which is greater than 0. So the root lies between 0 and 1. Fine. Also, if you want to find the smaller root, because we get a negative number, so let's say 0.5. So what will happen? If I found this number, you can check whether it's a positive or negative. If you find that, it will be my positive. Or you can check as the root is lies between 0 and 1. Or if you want to find as a 0.5, check whether it's a greater than 0, then the root is lies between 0 and 0.5. And if 0.5 is less than 0, then the root is lies between 0.5 and 1. That will take a less time. Now we can find the derivative of this function f, which comes to be here. Substitute this value at here, we can get this expression. If I take the LCM, does anything cancel out? Yes, this value will be cancelled out, so I can take the LCM as here. Now you can choose the any number in between 0 and 1. So let's say you can take as x naught is 1. Now how you can choose as x naught? One simple tips I can also tell you. You can find the intervals derivative value at the 0. You can find the derivative value at the endpoints. So when 0, it will be 1. When it is a 1, it's a 2 e raised to power 1. Which one is the larger? Which one is the larger? You can choose the root near to them. So clearly says absolute value of this must be greater than of this. So I can choose the initial root, that is my x naught, closer to the 1. I can choose x naught closer to the 1. You may choose x naught is 0.7, you may choose 0.6, you may choose 0.8 and so on. On the other hand, if this is less than, then we can choose the near to this like 0.2, 0.1 and so on. I can substitute this x naught at here, you will get this one. We can find the x2, we can get it. Now you can see in this question nothing is given to you. How many decimal places you need it. If nothing is given to you, then it is by assume you have to find up to the 4 decimal places. So you can see 4 decimal places are not matched. You can find the x4. Again you can see, now you can see the 4 decimal places are matched. So therefore my convergence is my here. Now as in the 4 example, you can see in each of the case we can get a convergent root. But when it will be the failure? This will be failure when you can choose the wrong x naught. How you can choose the wrong x naught? Look at this example. Now in this case, you can see the interval is already given to you, 1, 2. So it means there is no need to check f of 1, f of 2 and here. There is no need to check. So why there is a need of non-zero? Because clearly says 0 is the root of this. What is f of 0? Is 0. So 0 is my root, but we need a non-zero. So we can find the derivative. We can substitute this value in here. So if I take the LCM, nothing is to be calculated, cancel out. So we can write here. Now choose any number in between 1, 2. Fine. So how you can do that? The first way is you can find the value of this. Fine. And look at that which one is the larger, and then choose the value near to them. On the other hand, if I choose the value as say 1.1, which is nearer to the 1, if I substitute this value here, what is my x1? This x1 will be my here. Remember, the sine and cosine will be set in the terms of radian. So once you are finding the x1, x2 and x3, clearly says it's a decreases, then it's a increases, decreases. So does it convergent? It can never be convergence. So clearly says the equation method diverges. So once it's a diverges, it means you are unable to find the root of this equation. Fine, because you have chosen the x naught is my 1.1. On the other hand, if I choose x naught is my say pi by 3 is approximately here. So then if you substitute in here, x1 will goes to the infinity. Why? Because you can see what is my 1 minus 2 cos pi by 3. Cos pi by 3 is my half. So it will be my 0. So once this will be 0, it goes to the infinity. So therefore you can say what is the 1 minus, that means the derivative will be 0. So this means the method is not convergent. So the question arises is, can we obtain the solution of this problem? Yes, you can obtain the solution. For that, you can find the value of the f dash at the end point here and look at the larger one. Fine. So let's say I can find the initial value as 1.5. If I substitute 1.5 here, you will get this answer. If I substitute this x1 into this, you will get this answer. Now you can see they are near to them. If I found the x4 and x5, you can see up to the 4 decimal places they are matched. Hence, the root of the equation is by here. Look at the another one. Apply the Newton methods to find the root where 0 is my exact root. Does this convergent? If so, what will be the rate of the convergence? Now you can see there are the two cases. We can find the two cases for here. So when x is my greater than 0, then what will be my fx? Then fx will be my root of x. What will be my f dash of x? It will be half x raised to power 1 by 2. This is my f dash. I can substitute both values at here. You will get this expression. Now if you simplify them, it will be xn minus 2xn. So what is that? This is my minus xn. On the other hand, if I take x is less than 0, then your fx will be my minus of root this. Then you can find the derivative of this. It will be half minus of this of minus 1. That is half of root minus x. I can substitute both the values at here, and after the simplify you can get this expression. Now clearly says in both the cases we will get this one. Does it convergent? Does it converges? Because you can see, does it converges? So when it will be convergent? Either you can take the x0 some point, find x1, find x2 and so on. But on the other hand, we all know the ratio between these two consecutive terms, if it is strictly less than 1, then it is convergent. Fine. This we all know by using the ratio test. Fine. And if you consider it's a greater than or equal to 1, then it is my divergent. So if you take the ratio of this, what will happen? You can see the ratio is 1, which is greater than or equal to 1. So therefore this sequence provides no convergence. Or you can say this sequence is my oscillating because of negative. Suppose x0 I can consider as a 0.5. What is my x1? Minus 0.5. What is my x2? Plus 0.5. x3 minus 0.5. So that's a oscillating sequence. So provide no convergence. Look at the another one which is similar of this. Does it convergent? Again, when x is greater than 0, your f will be x raised to power 2 by 3. Your derivative will be 2 over 3 x raised to power minus 1 over 3. I can substitute here. You will get this as the expression. For x is less than 0, your f will be minus x raised to power 2 by 3. Derivative will be minus 2 over 3 of this. I can substitute both the values here, and after the calculation you will get this. Now in all the cases you can see you will get here. So does it convergent? You can see xn plus 1 over xn. What is that? It is half, which is less than of 1. So therefore it is convergent. Now we can find once it's a convergent. So our target is to find at what rate, whether it's a quadratic rate of convergence, linear rate of convergence, or others. So from both the cases what we can observe that xn plus 1 is here. Now since our target is to find the rate of convergence, so we need to express in terms of error, that is xn minus alpha, where alpha is my 0. It is already given that alpha is my 0. That means we need to write each term where the xn appears in terms of xn minus 0. So I can write easily in terms of here. Clear? Now what is that 0 is? 0 is my alpha, because this is my root of the equation, so which come to be as here. Now what is that? This is nothing but my error at the n plus 1 equation, and this is my error at the nth iteration. So what does it means? E of n plus 1 is proportional to of this. Now what will the power is? Power is 1. So what is the meaning of that? It means the rate of convergence or order of the convergence is my linear. So we can say the order of convergence is linear. So once it's a linear, we can say the progress or convergence is my very slow. Remember, if instead of this alpha is 0, if some another sum is given to you where alpha is 1, then you have to express each term in terms of minus 1. So how you can write? So you can see it is a minus 1, so I have to minus 1 here. It is a minus of half. I have to add this term, and then again you can see now this term is my e of n plus 1, this term is my e of n, and of this nature. So this is the way you can proceed for the rate of convergence. Okay, look at the one more example. Find the real root of this term up to the 4 decimal places. Again, the interval is not given to you, initial point is not given to you, so we can firstly find the initial point. So clearly says what is a f of 1. F of 1 is log 1 is 0, it's a minus is a 0. F of 2, it's a 2 log of 2 minus 1.2, again it's a less than 0. We can find the value of the f3 and so on. You can see f2 is a less than 0, f3 is my positive, so the root lies between here. We can find the derivative, which is the derivative. You can take the product rule here. Now this will be cancelled out. So what is the value of the log 10e? It is 0.4343 up to the 4 decimal places. Substitute this value here, you will get as this expression. Now choose x naught, any value in between 2 and 3. So I choose x naught is my 2. Then I can substitute here, you will get x1, x2, x3 and x4. So clearly says up to the 4 decimal places the results are matched. So we can say the desired root is my this. Look at the another one. Show that the following two sequences, this and this, both have the convergence of the second order. What is the meaning of that? Your target is to prove of this nature. This is our target to prove that. Fine. Now what is my en plus 1? En plus 1 is xn plus 1 minus alpha. Root is my here, and e of n is my xn minus of root this. This is our target. You can see about the modulus value. This is given to you, which is given to you, and your target is here. So that's very simple. We can start from this part. I can this is for the first part. I can subtract the minus of root a on this, so which is here. I can open this bracket, which comes to be this value. Now what is that? Is it something square? Yes, this is a minus b whole square, which is to be. Now you can take the LCM. Once you take the LCM, it will be here. So what is that? This is nothing but my, since root is my root a, and this is my e of n. So clearly says I can return after that en plus 1 is proportional to e of n square. Because of this 2, it is of the second order convergence. Similarly, we can check about the second part. We can start from here. We can subtract minus of root a. So we can write. We can open this one, which is written to be this nature. Because we need the value of xn minus root a. I can make them because of this 3 by 2xn. I can break them is half of xn plus of xn. Half I can adjust here and this one. Now you can take the LCM of this to be here. Can I write this expression as root a square minus xn square, which comes to be a square minus b square, a minus b, a plus b, because we need this expression. So I can substitute here and I can take the common, so which can be written here. Now I can open this bracket, which comes to be this one, or you can take the LCM. Does it expression anything? I can take as a minus common. It is of divided by 2a into xn square plus xn root a minus of 2a. So can you factorize them? Yes, you can easily factorize them. It's a root a and the 2 root a. So it is, you can simply factorize them. It comes to be here. You can factorize them to be here. Fine. So once you factor them, you can get as this expression. Now clearly says this is my en plus 1. So the left hand side is en plus 1. This is my en divided by 2a. This is my en and this is my number as here. So I can return this as en square. So this value, or after that I can return this number is proportional to en square. Because of this 2, it is of the second order convergence. Look at the last example here. Apply the Newton's formula. Find the recurrence formula for the nth root of alpha. This one. Fine. So once you are using here, then what will be your f? If you are written alpha as here, this is my f, then what will be my this f upon f dash? If I substitute this value, what is that? This is x minus of this. Derivative will be 1, because what is the f dash? Is my 1. So clearly says xn will be cancelled out. It will be alpha raised to power n, which is independent of the x. It means it will never be suitable. So I can rewrite this equation as of this. I can simply write that. Now I can consider this is my f. Then we can find the derivative. We can substitute this value in the Newton-Raphson method. We can take the LCM, and this is my required recurrence formula. Now based on this formula, you can find the value of 240 raised to power here. So if you compare them, n is my 5, alpha is my here. Now what you can take as the initial guess? There are the two ways. First of all, you all knows 2 raised to power 5, which is 243. Fine. So it means, and it's a 240. So what is the meaning of that? If I, or you can simply take f of x is x raised to power 5 minus 240. So what is the f of 1? Is a negative. F of 2 is a positive. So the root is lies between 1 and 2. And how you can choose the x naught? You can check about their derivative. Add the 1, check at the derivative 2. What is my f dash? 5x raised to power 4. So it is my 5. It is 5 into 16. Clearly says f dash of 2 is greater than of f dash of 1. So I can choose the x naught which is nearest to the 2. So I can choose as a 2 or 2.9. Anything are there. Now you can see, once you can substitute x naught is my 0.9, 2.9. I can substitute the value here. N is my 5. Alpha is my 240. You will get x1. Once we can substitute x1 here, you can get as a x2, x3 and x4. Clearly says up to these values are accurately matched. So your desired root is my 2.993 up to the 3 decimal places. If you want to write up to 4 decimal places, then you can write as a 0.9925 is the required root. So this is the way you can solve all these questions in very simple manner. We will come up with the second part of this Newton-Raphson method, where we have explained the different kind of the examples for here. Till then, you can simply like, share and comment on my video. Best of luck students. Happy learning always.